Okay, so let me remind you of what is, I will dub it conjecture A because that's the form I came into acquaintance with it. But it was initially, I think, formulated for surfaces, and we are going to do threefolds, at least as an aim of this talk. So let me state a version of it. As usual, it's very imprecise. So let's say Q-Fano threefold X of dimension n modulo deformation. It's in one-to-one correspondence with certain, and there was a lot of discussion about what certain means. Again, even the previous talk, Laurent polynomials. So F in n variables, quotienting by mutation. Okay, so you've seen this both in Al's talk and in Andrea's talk. We won't be dealing with the affine case here, and we won't even necessarily be dealing with the Gorenstein case here. So the goal here is to construct Q-Fano threefolds. So this one-to-one correspondence, again, as it was already mentioned, corresponds to a deformation. So either a smoothing or a degeneration, depending on the direction in which you're looking at. So let's say, so there's a bit more geometric content. Let's say that the Newton polytope of F is called P. This turns out to be a Fano polygon. Sorry, polytope. Right, and then you build the toric variety XP, and then this smooths to X your Q-Fano threefold, more or less. This is what is called a QG smoothing that preserves, well, I'm putting this in inverted commas, so minus K, but the entire Hilbert series, in fact. So this is what we are dealing with. Something that I would like to add that I think was not mentioned here. So again, there's 600,000 of them. If you assume that XP is canonical. And this, again, there's a conjectural classification, so we don't really know if they really exist. Again, I'm finishing with what Al finished. So there's 500,000 different Hilbert series for such Q-Fano threefolds. There's a bit more data that is derived from these Hilbert series. So it's not just minus K, but also from this you derive the expected codimension. And actually, it gives you the expected anti-canonical embedding of, so into weighted projective space. And then singularities that you expect X to have, okay? Because clearly we are going to want to find singular varieties, right? Because yeah, Fano threefolds that are smooth have already been classified. So yeah, we don't, that's not what we're looking for. Right, and the expected codimension into weighted projective space for most of these guys is quite high. In the sense that if you have such a person, you don't really know how to construct it in order to make sure that it actually exists. So there is no way to write equations. So current graded ring methods only work up to codimension. So when I say graded ring methods, again, I kind of mean writing equations explicitly. Up to codimension Well, I'm going to put 4 here, but actually there's some work of Tom Duckett in codimension 5, and there's a bit of work there. But in practice, what appears in the database are things that go up to codimension 47. So that's not really, yeah, codimension 4 is comparatively quite small. Okay, so the goal of this talk is to show you that I can find constructions up to codimension 19. So I have examples up to codimension 19. Okay, so let's see why Laurent inversion. What are we actually trying to invert? So again, this is either a smoothing or a degeneration, and work has been done to find an algorithm going from left to right. So if X is a complete intersection inside a toric variety Y, then so there exists an algorithm to build its Landau-Ginzburg mirror, so its model, Landau-Ginzburg model, so its mirror, to build the Laurent polynomial, or a Laurent polynomial. Mirror to it, so via this correspondence. Let's see an example of how this works. So we've already seen this in the case of projective space in any dimension, and in particular, Al wrote the Laurent polynomial for P2, so I'm not going to write P2. I'm going to do it a little bit more, in a little bit more difficult case, but not too much. And also I'm just going to like splash the result in your face without justifying why it's there. So let's say that X is a hypersurface of degree 6 in P1, 1, 2, 3. So this is a surface. This is so Fano surface or Del Pezzo surface. Of degree 1. And by work of Kiventhal and Horivafa, and also a trick by Krzyżalkowski. Oh no, there's a J. Yeah, I've written this name like 100 times in the past 2 years, and I still don't know how to write it. Okay, so these feed you the fact that the polynomial f corresponding to this person is, well, a polynomial in, since it's a surface, it has to have 2 variables. So it's, let's say they're A and B. This is the person, and then A squared, sorry, times B cubed. And again, this is a bit, I'm not sure it's very edifying because I'm just giving you the result without showing you exactly how you get here. But I'm just making a point that this sort of encodes the degree of the surface and kind of the significant weights of the ambient space inside of the polynomial. I'm also going to say something about what happens if you are a complete intersection inside a higher. So if rho of y, so here rho of y, the Picard number of the ambient space, is equal to 1. If this increases, is larger, we add, and add is an important idea because this is not going to be multiplication of this kind of Laurent polynomials, like you have seen in Andrea's talk when there was a Minkowski decomposition, but this is a summation of factors. We add more summons. So more summons will appear to the LP, in the LP. Okay. Also, maybe it's a nice thing to remark about what the Newton polytope of this guy looks like. So its Newton polytope is, well, let's see what's this. So A plus B plus 1's Newton polytope is simply this triangle. So it's a simplex of volume 1. Then if you put it to the 6, it's going to be a simplex dilated 6 times. So the same simplex dilated 6 times. And then if you quotient it by A squared times B cubed, it's just going to mean that the origin is moving from this corner onto somewhere inside of the polytope. So indeed, this is going to be what I wanted to say here, what I wanted to call here a Pfaffian polytope, because it contains the origin and its vertices are going to end up being primitive vertices. Okay, so what I'm saying is that this, the phase span of the polytope that is the support of F is going to correspond to a toric Fano variety. Okay.
Is that two-dimensional or three-dimensional?
It's 2-dimensional here, right now. Everything is flat. Okay. All right. So, but this still looks like quite a basic type of polytope that I have obtained here, right? It's just a dilated simplex. And I'm going to make the point a bit later that when you add these these other summands into the Laurent polynomial, they are also going to have some sort of this basic kind of shape. Okay, or simple kind of shape. All right, so their Newton polytopes are going to be like this. All right, so now we're going to try to go the other way around. Start from a Laurent polynomial and try to build a complete intersection inside of a toric variety of arbitrary Picard rank. So, and since we are trying to sort of move the other way, this is called Laurent inversion. Because we are effectively trying to invert this algorithm here and find the correct way to do it. Okay, so the motto of this is to embed. So you have two varieties. You have two varieties, XP, and you want to get a variety X, which is a smoothing of XP. So the motto is to embed XP. So start with, with F, a Laurent polynomial, and build XP, the toric variety associated to its phase span. The motto of Laurent inversion is to embed XP inside a larger toric variety and try to smooth it there. Okay. So let's try to do that. Well, we'll do that on a running example because there are quite a few definitions. So I will just illustrate what happens in each case. So the running example is going to be this polytope P. So let's say that I'm in a slightly more dilated lattice than what the squares here suggest. Let's say that this is my polytope P. Okay, P lives in some lattice N. So this is a Fano polytope. I'm yet again going to give you a surface example first because it's much easier to follow. Then XP given by its phase span. I'm saying that this point here is the origin of the lattice. And then let's also denote by M to be the dual lattice of N. also called its character lattice. Okay. Another part of the setup is Z. So this is setup. This is in general. The second part of the setup is Z, which is an auxiliary object, a smooth toric variety whose character lattice is N. Therefore, if you think about the fan of Z, it lives in M. So this Z, this auxiliary object, involves a choice. I have to choose who Z is. And in this case, in my example, I will choose Z to be P2. And I will now draw the fan of P2 inside of its ambient lattice, which is M. So let's say that this is my ambient lattice. We all know what the fan of P2 looks like. We've seen it even today more than once. Let's say that this is the origin, and then this is the fan. And that's it. So far, I'm just looking at two toric varieties. Definition. Each fan lives in the other's character space. So a scaffolding S of P, so of the polytope that we start with shape Z, the auxiliary shape, is a collection of torus invariant Neff divisors on Z. So this is very important. We call this S person, we're just going to denote it by di. I is an I, such that the convex hull of the polytopes associated to the di in I is equal to P. So why am I saying this? Well, okay, if you think about, just basic toric geometry for a minute, since I'm taking Neff divisors, and I should in fact be taking an even slightly stricter condition here, but since I'm taking Neff divisors, then each of them will have a non-empty polytope associated to it. It could be a point, but it's definitely not empty. Where do these polytopes live? Where these polytopes live, all of them in the character lattice of the variety we are considering. But these are divisors on Z, so P of di will all live inside of N. And then the additional condition is just that the convex hull of all these polytopes is in fact our initial guy P. So this involves yet another choice of who are these di. Let me just denote these rays by row 1, row 2, and row 3 in order to be able to actually make a choice in the example. Maybe a bit more of nomenclature here. So each PD, so each of these pieces, associated to these divisors is called a strut. And yeah, as you know, Z is called the shape, as I put it here. That's fine. So in our example, choose, let's say, two of these guys, one divisor D1, one divisor D2. As we know, these are torus invariant divisors, so they will be written as combinations of the divisors corresponding to each ray in Z. So you will not be happy about me denoting it like this, but I will denote these C1 and C2 as because they are curves for Z, as the divisors corresponding to row 1 and row 2. D2 will be C3. You notice that this guy is in O of 2, for example. On P2, this guy is in O of 1. I don't know. This looks pretty familiar so far. Okay, and now to make sure that this is a scaffolding, I just have to draw the polytopes associated to D1 and D2 inside of N, so this part here. And you will have to believe me that this is P of D2, and this is P, oh, that's a very straight line, P of D1. And you can see that their convex hull does make up for my entire sort of square with the cut corner over there. Since so indeed, this is a scaffolding. Okay, so if you just read this for the first time, you're kind of, I mean, I know you're not reading this for the first time because I've already sort of given a version of this talk before, but you're going to wonder why are we doing this? Like, what's the point of just looking at this object in the dual lattice and what do you want to do with it? Well, the point is that you have to keep this motto. You have to consider this motto. Our goal, our ultimate goal is to embed XP. So why are we doing this? Write the ray map for Z. Right, so the ray map just takes Z to the number of rays of Z, which is 3, onto Z2, and this is going to be surjective in this case. The ray map for Z is just 1, 0, 0, 1, and minus 1, minus 1. This Z2 guy for us is M in our notation. Dualize it. If you've ever worked with toric varieties, you see this as part of short exact sequences all of the time. So you have Z3 dual, Z squared dual again, which is going to be N, and this is 0. Then if you tensor it with C star, you get torus of N injecting into Z to the, well, if I denote number of rays of Z with R, this, even in general, even not for this example, it's always going to be Z to the R dual. And this is another torus. So this is the torus, which is dense, in XP. So there's a bit of a, left and right juggling here. We started with an object whose fan lives in N, and this is the object that we care about, XP. This is the object that we're trying to say something about. We chose this object in the other lattice, which helps us by writing the usual GIT short exact sequences to build it as a GIT quotient, which helps us to embed our torus. So most of our toric variety is already taken care of by being embedded into a larger torus. So Tn compactifies to XP. So the idea is to find a compactification of, sorry, not Z to the R, C. C star to the R. To find the compactification of C star to the R, such that XP is a complete intersection there. So in other words, again, build a larger toric variety such that XP is a complete intersection inside of that. Okay. And indeed, this is the theorem of the Laurent inversion paper. So the theorem, this is work of Coates, Prince, and Kaspczyk. See, I got this name right. Which is given a scaffolding, so the previous setup, S of P, there exists a torus invariant embedding of XP inside a toric variety Y. This contains C star to the R number of rays of the auxiliary shape as its torus with rays of the fan of Y, this larger space. So E, let's say I, maybe I from 1 to R, a standard basis of Z to the R, and minus DI, given that when you build, again, this short exact sequence, which is the short exact sequence starting from the character lattice of a shape Z, like this, what you obtain here is nothing else but, so what I obtained there, which is ZR dual, is nothing else than the group of torus invariant divisors on Z, the variety that I started writing the sequence for. The torus of Z is Tm. And again, if we know a bit of toric geometry, we know that this is just generated by the Ci, the divisors corresponding to the rays in the fan of Z. Okay, that's a whole lot of stuff. Let's see how this theorem applies to the example that we started with. So for the example, so you might remember who D1 and D2 were. So D1 was C1 plus C2, D2 was C3. So I take a so who are the rays of the ambient space that I'm building? So I have a standard basis of Z3. By the way, we are embedding our surface into a threefold. 0, 1, 0, 0, 0, 1. I took the standard basis. And now I have to see what happens to two more rays that each correspond to the DI that I chose. So minus D1 is going to be -1, -1, and 0. And the other one is going to be 0, 0, and -1. Are the rays of sigma Y in this case. So now the question is, who is Y? Who is the threefold that has these rays? Whose fan has these rays? And you're going to also ask, maybe, is there just one threefold? Because sometimes for threefolds, the cones determine the variety and there is not a unique choice of cones, but in this case, there is one. And
it's a blow up?
No, it's not.
Oh.
It's not a blow up, it's a product. This is not the weight matrix. This is just the rays of the fan, okay?
Okay, thanks.
So in a weight matrix, there will be such things appearing and then you could conclude that it's a blow up, but this one is not. So, whoops, sorry guys. Y is simply P2 cross P1. You can recognize the fan of P2 here. We've already seen its rays, and you can recognize the fan of P1 in this bottom block. Anyway, so what have I done? If this has coordinates x0 to x1 to x2, and this has coordinates y0, y1, what have you obtained? The theorem also tells you the following. So XP is going to be a hypersurface in this threefold, right? I started with a surface. Tells you that XP is a section of O to 1 in Y. Okay? And the question is now, who have I built? So who is a, and now our X will be obtained by just taking a general section in O21. So a general section has equation, let's say, polynomial of degree 2 in the x-axis times y0 plus polynomial in degree 2 in the x-axis times y1 equals 0. Now the question is, who is the inside of P2 cross P1? Well, the variables x and y are completely independent. So this looks like a blow up of something. And it precisely looks like the blow up of the intersection of the equations F2 and G2 inside of P2. So X is the blow up of P2 in, well, two conics in P2 intersect in 4 points. So we have obtained an embedding of the Del-Pezzo surface of degree 5 inside of P2 cross P1, okay? Just by using this construction. So I have dropped codimension. Usually this is, if you embed it with anti-canonical, I think it's codimension 3, and I have dropped it to 1. This is not a big deal because, again, I did it just in the case of surfaces and it's not huge. But in general, this construction, just choosing an auspicious auxiliary shape and an auspicious scaffolding, so sort of separation into bits of your polytope, helps you with a lot of classification problems. In particular, so I guess remarks. This is very helpful in general. So I first started being acquainted with this method when Alessio and I wrote a paper in 2015, and it was all about classification and finding certain models and finding certain surfaces. And there was one surface that we just could not find, and we got stuck with that point in the classification for more than 1 year until Thomas Prince, Tom Coates, and Al came to us and just basically gratuitously dropped us this surface in our laps without us having any idea where it came from. And like, we tried to build it using birational techniques is what I'm trying to say, that somehow this construction completely bypasses any kind of birational properties, sometimes even graded ring properties of the toric object that you start with, and just builds this guy without, like, and offers you basically coordinates and offers you ways to deform this by just adding more monomials to your section. So it's very easy to obtain a complete intersection, a general element in a complete intersection, because the deformations are unobstructed. Anyway, so yeah, it's very helpful. So see a third 1-1 paper. Another remark is that this is much harder for threefolds, which is kind of the leitmotif of the day. For threefolds, but it pays off. And it pays off not only, maybe if you remember the beginning equivalence here. So if you remember Al's talk, Al said there are 50,000 here. Don't know how many of these exist. How many Hilbert series exist? So are basically materialized, incarnated in this Q-Fano threefold, but also don't know if a Hilbert series exists, how many non-deformation equivalent Pfaffians we have for a given Hilbert series. So don't know how many Pfaffians for a fixed Hilbert series. And I guess a hint here is, again, how many deformation components there are. You can find this in Al Kasprzyk's talk. But yeah, there's quite a few hints that we can build quite a few of these by using this technique. Because basically, even if you've identified deformation component of your toric variety, so smoothing component of your toric variety, where smoothing is again with inverted commas, you don't know if you can actually find a Q-Fano person there until you've actually built it. Okay. So the difference between what we're doing for surfaces and what we're doing for threefolds is basically the fact that now the deformation space can be obstructed and there can be various components of various dimensions, and we don't really know where to go. Okay, so something else I would like to say is that, sorry, in this example that I made, I basically, kind of chose to forget about the Laurent polynomial itself, and I just talked about the toric variety XP, and I just, decomposed its polytope, etc. But in fact, the Laurent polynomial is present in this construction. I just gave an easier version of this construction, but in what I did, so if you remember, I did something like this. I split it into these two triangles somehow. But the Laurent polynomial, which is supported on this polytope, actually has the binomial edge coefficients that you are used to since Andreas' talk. And in a way, these simplices that come here come with their own coefficients attached. So here we have 1, 1, and 1 for each of these points. And on the dilated person, we have corresponding, I'm going to enlarge this, corresponding coefficients. 1, 2, 1, 2, 1. So that now when we sort of put the green coefficients together and we add them, what you obtain has to match the coefficients on the big polytope. Okay, so I would like us to now look at an example, a concrete example of what I have to deal with every day. Okay, so we're going to do we're not going to do the baby version anymore. So we're going to do a grown-up example. And I'm going to take advantage of the fact that we are at a distance and I can show off a bunch of programs that I'm working with. And so say hello to JMOL, a polytope visualization program, which is, has this kind of unsightly color associated to every polytope, which you can see here, but fortunately allows me to move it around so I can see how these pieces, so the equivalents of the triangles that I drew here, I can now see how these pieces are going to fit inside of my big polytope. Okay, so when I usually start my analysis, I start with this kind of a person. Can you see it? Is it visible? Yes, no. Everybody's asleep.
Yes.
Ah, cool. Thank you, Mark.
Takes a while to unmute.
Okay, so in my life, I usually encounter just a very, squished version of this polytope. Now I have to look at it carefully enough and to decide.
Why don't you talk us through it? The base The base is a regular hexagon.
Yes,
Top
the base is a regular hexagon, and
top
then
is a regular triangle.
exactly. So
And why does that back face not go up to the top? Is that a mistake of graphics?
no, what do you mean? It just, this is the polytope. I should have,
Yes, the triangular faces, the diagonal triangular, the side triangular faces.
you mean this
One
one?
of them, two of them go right up to the top, and the other one goes only halfway up. Goes only 2/3 of the way up.
Yeah, but because that's what the polytope looks like. Yeah.
Good.
Okay. So yeah, this one in particular, as Miles said, we just have to look at the coefficients that are not zero. Okay. So as Miles said, there is a regular hexagon at the bottom, and then there's a bunch of zeros here in the middle, and then there are two triangles like this up here. Okay. And now what we have to do, okay, I'm giving you a view from the top, a view from the side. This is pretty symmetrical if you look at it, but it is in no way extremely nice. Like this is, for example, not a Gorenstein polytope. These singularities, well, they are isolated if you look at them, but they're not like particularly nice. You can see something that you recognize down here because you've seen it all day today, but yeah, there are some lattice points here on the side that you don't recognize. There are some inner lattice points of this polytope. It's not canonical, you know, it's not like the best, you know, your best friend ever. But still, it's quite easy to use this construction on it. Can you guys still hear me? Because my video stopped for some reason.
Yes.
And
Yes.
yeah, okay, cool. Thanks, Cassie. Okay, so now we're going to have to eyeball who Z is here. So who is my auxiliary shape whose sort of polytopes or, okay. I have to nail the shape so that its moment polytopes, so its polytopes associated to its divisors and including its moment polytopes, fit somehow inside of my polytope here, and not only fit, but fit optimally somehow. Like I have to really try to put the minimum amount of struts on it. And so maybe you'd like to take a guess, or maybe you'd like me to tell you. So there's clearly a triangular thing here going on, which Miles already pointed out, okay? So there's clearly some either P2 or blow up of P2 in one point happening, okay? There's also the fact that here there are two exactly identical triangles and they're one on top of each other, which kind of suggests that you want to put them both into just one polytope. So just one PDI, okay? So any suggestions? Should I move it more around so you guys can see it in a more, you know, easier way? Will it help you? Okay, going once, going twice. Okay, I'll tell you. So in the grown-up example, the shape Z is going to be P2 cross P1. Okay, so I'm allowed to use what kind of shapes? So I'm allowed to use the moment polytope of P2 cross P1. I'm going to put it vertically. It looks like a triangular prism. Okay, this is precisely what will take care of all these ones on top of my polytope. And then I'm also allowed to use, this is the moment polytope, I'm allowed to elongate it as much as I can, and I'm allowed to make it as flat as I can. So the flat version of this is simply a 2D triangle, which I'm also allowed to use. Okay, everybody following so far? So what I'm going to do is, again, put this guy on top. And then this triangle, I'm going to use it. So now that if I look vertically on the hexagon there, I'm going to obtain exactly the decomposition that Miles was talking about. Everyone? Yeah, which is this. Okay? So basically, I have one guy here, which is a 3D person. Now I'm going to look at it from the top, like this. So I have this 3D person here, and then I have the usual, you know, triangular scaffolding of the hexagon. Okay? So, okay, first question. Where am I going to embed this? Is it clear to everyone what I'm doing right now? Hopefully, from this drawing here. So these are all are flat. So XP, which is again a threefold, because it comes from a polytope of dimension 3, is going to be embedded in the fold Y as a codimension complete intersection. Okay. So how big is Y? I will scroll a bit up so that you can remember the theorem here. So XP will be embedded in Y, which will live in a lattice of dimension R. I'm sorry, this should not be blue. It should be something nicer. In dimension R. R was, as I denoted somewhere here, the number of rays of Z, my auxiliary shape. How many rays does my auxiliary shape, P2 cross P1, have? I wrote them, I listed them, they are here. How many rays are there? 5. So Y is a 5-fold, and I have embedded my threefold X into a 5-fold as a codimension 2 complete intersection. Okay, so now I'm going to write, so in general, we'll write Y as a GIT quotient, because it's much easier to work with equations and to check that the singularity content is correct. So I'm going to give you what GIT quotient I will get from here in this case. So I'm going to have an identity block, which unfortunately I will have to write for what is good for me later. I hope I'm fast enough. And then I'm going to give you another 5 rays. So another 5 columns, sorry. -1, -1, -1, 1, 1, 1. Should have had this pre-written, it would have been so much better for me. -1, 0, 1, 0, 1, 0, 0, 1. So these are not the rays, but these are the Cox coordinates, okay? So I'm just going to write this as x1, x2, x3, blah, 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 until x9. And then the line bundles, I'm gonna write them all have homogeneity type, 1, 0, 0, 0, and 1, 1, 1, 1. Again, this is just a byproduct of the construction, which will tell me what to put here. What else do we notice here? Well, okay, L1 is the same homogeneity type as x1, the coordinate. That means that when you write the equation of L1, it's going to start as x1 plus something, okay? So you can just basically solve for that x1 and get rid of this guy. And it's even better because instead of embedding the threefold into the 5-fold as a codimension 2 complete intersection, if you get rid of this coordinate, you can actually XP is a hypersurface here. And now, you know, we're pretty happy about this because if you look for who the polytope corresponded to in the database, you get something that was initially codimension 13 in its anticanonical embedding. And we have built this codimension 13 person as a hypersurface in a fourfold that is a toric variety. So that's a pretty big jump. So what does this do? What can we conclude from here? Well, first I'm going to just show you the table of all of the examples that I have so far, which are not that many. There's a bit less than 40 of them, but we are going to look at them together and conclude. So this is the table. Can you guys see the table? Hopefully, yes.
Yes.
All of these Q-Fano IDs means that it's a different Hilbert series for each of the people here inside of the database. For this entry, for example, there are two different Q-Fano threefolds that I find for the same Hilbert series. They have different period sequences. Therefore, I have generally found two varieties which are not deformation equivalent, but they have the same singularity shouldn't say that, singularities and codimension and, you know, genus degree, whatever you want. The constructions are fairly different. This second one is, for example, a codimension 2 complete intersection. It's exactly the same notation that I have used here. Okay, so just Cox coordinates. This person here, which is a huge matrix, is actually just given by Pfaffians of a matrix. So basically you have 5 line bundles that intersect, but do not give a complete intersection. Lots of the other ones are just complete intersections. And notably, Pfaffians are much harder to check the singularity content of. So, you know, we're happy with all of them technically. So sometimes I find, for example, this 37847 guy, I have found it four times in total. Only this, so this guy means that two Laurent polynomials are based on the same polytope. This is a polytope that is mutation equivalent to this, but combinatorially, on which there's another Laurent polynomial going into another direction. And this goes into yet another direction. All of these 4 period sequences, this one, this one, this one, and this one, are different. So that basically what is happening here is that I found something kind of like this. Let's say that this is a component of the deformation space. This is another component of the deformation space. This is yet another component of the deformation space. Okay, so I have sort of 2 surfaces and 1 curve. I have no idea in reality what the dimensions of these spaces are. So basically I have a toric person here, another toric variety here, and let's say another toric variety here. I can move, so from this guy, let's say this is the one with 2 Laurent polynomials, I can move in 2 directions, and I find x1 here and x2 here. But then I have another polytope, which is, let's say it's this one, let's say the green one, and I can move in another deformation component and find x3 here. And independently, I am moving in yet a 4th deformation component, and I can find x4. So these are all suggested simply by the different period sequences that you can put on all of these polytopes. So ideally, if one would make a very systematic search for these things, like Al said, the real hint to how many Q-Fano threefolds there are is in fact the period sequence. It's not the number of entries in the database necessarily, or anything like that. These are sort of telling you where to look, but they can never tell you how many varieties of the same type there are in one of them. Okay, so I guess that's all I wanted to say for now. Thank you.